All right, Basil. What we're going to look at is we got 1.1, and I'm going to look at number 25, and this should help you with both 24 and 26 because it's basically the same process. Be careful with 24 and 26 because they're going to utilize derivatives for their initial conditions, but we don't have to do that for this particular one. So we've got a 5 foot tall boy, and he tosses a tennis ball straight up from the level of the top of his head. Neglecting frictional forces, the subsequent motion is governed by the differential equation d squared y dt squared equals g. And so we've got d squared y dt squared equals g. And the g that we're going to use here is going to be 32, or actually negative 32, because it's going to be heading straight downward, okay? Because up, right? And then it's going to head downward. So negative 32 feet per second heading towards the ground. And that's our acceleration due to gravity. And the reason why we're going to use the negative 32 feet per second squared is because our boy is 5 feet tall. Okay, so our unit of measure is in feet, so consequently we're going to use the feet acceleration. By the way, the 5 foot tall boy actually gives me one of my initial conditions. If y is my height, okay, so y is my height, that's actually going to be my function that we're looking at here, then y of 0 is going to equal 5. Great, right? Because at 0 seconds, the height of the object is going to be 5 feet. Now, the next thing that we need to get is that this is acceleration. So how do we find velocity? And then how do we eventually find height? Because we need to get back to a function for height to find a max height and to find the time for the max height. So how are we going to do that? Well, what we're going to do now is we're actually going to go in here and we're going to say, okay, well, I know that dy dt, the first derivative of y, if y is the height, and d squared y dt is acceleration, in between there, we're going to get velocity, right? The first derivative is going to be velocity. And so what I'm going to need to do is I'm going to need to integrate. The idea here is that if I have a second derivative and I need to get to the actual function, what do? You integrate. Okay, that's the antiderivative. The idea. So what I'm going to do is I'm actually going to go in and I'm going to use that. Now I need another piece of information. And the second piece of information is if the object hits the ground 8 seconds after the boy releases it. That's perfect piece of information because that actually tells me that at 8 seconds, y of 8, because t is 8, I'm going to be at 0 feet. So y of 8 is going to equal 0. I'm going to hit the ground. Now, given that's the case, that actually gives me the 2 initial conditions that I'm going to need because I've got the second derivative. When you use the second derivative, that's what you're going to need. Okay, so here's what we're going to do. I'm going to take the derivative first of negative 32, my acceleration dt. And that's going to end up giving me dy dt. Take the first derivative, the integral of d squared y dt, you get dy dt. And so this ends up being negative 32t plus some constant c1. Awesome. Now I'm going to find y, and how I'm going to find y is I'm going to take the derivative again, the integral again. And that's the integral of negative 32t plus c1 dt. And that's going to end up being negative 16t squared plus c1t plus c2. Okay, and that's just straight power rule. Now, this is the function for height. I need to find c1, I need to find c2. I'm going to use my initial conditions in order to do that, just like we've seen in our initial value problems. This is a straight initial value problem with just a little bit of extra knowledge thrown in there. So I'm going to take that, and that means that if I take y of 0, that's going to equal negative 16 times 0 squared plus c1 times 0 plus c2 equals 5. And if I simplify, I get that c2 is equal to 5. Okay, you can see that you're just multiplying stuff by 0. Now I'm going to use y of 8 to find c1. So y of 8, which equals negative 16 times 8 squared plus c1 times 8 plus c2, or plus 5, which is what c2 is then going to equal 0. So I go in here, and then that means that this is negative 1024 plus 8c1 plus 5 equals 0. Doing a little algebra, right? Just straight algebra. I get 8c1 equals 1019. And so c1 ends up equaling 127 0.375. With C1 and C2 now, what I have is I have my function. My function for the height. The function for the height is y of t equals negative 16 t squared plus 127.375 t plus 5. And there's the function for the height. Sweet. Okay. All I need to do now with this is I need to now go in and I need to now find the maximum, the time at which I hit the maximum height. Well, this is a parabola. And the maximum height for the parabola is going to end up being the vertex. So we'll use the vertex formula. So the vertex formula gives me that t value in this case is going to be negative b over 2a, which equals negative 127.375 divided by negative 2 times 16, or 2 times negative 16, excuse me. And that ends up giving me 3.9805 seconds, which makes sense because the boy's throwing the ball from his top of his head, and that's 5 feet, okay? And so the ball is actually going to be traveling downward a little bit longer than it'll travel upward, okay? Because it starts up higher, ends up lower on the ground. Kind of makes sense that it'll be around 4 seconds, but not quite 4 seconds. So now what I need to do is I just need to input in this time into y. So you take y of 3.9805, okay? You plug it into this function, and then that gives you your maximum height. And I'll let you go out and do that on your end, okay? So what I got here, this is how this is going to work. We notice that d squared y dt squared is the acceleration due to gravity. The first derivative, or the first integral away from the acceleration is the velocity, and take an integral again, and I end up with height, right? Because if y of t is height, its first derivative is going to be its velocity, and its second derivative is acceleration. So in order for us to take the acceleration equation to the height equation, you've got to take that integral twice, right? Once for the velocity, once for the height, okay? And once we get there, we need initial conditions. Since I have a second derivative, the initial conditions are going to be derived from, I'm going to need 2 initial conditions in order to get my two values, C1 and C2. Once I do that, then it's just a matter of just some algebra in this case. Or you could use calculus, where you take the integral and take the derivative and set it equal to 0 and see what you get there. It's going to be the same value. All right, I hope that helps.